Biostat 6611, skills for the rest of your life. Bootstraps and probability. It's the bread and butter, baby. What's your jam?
Greetings, Bios 6611. For this lecture set, we're going to jam out to some probabilities, joint, marginal, and conditional. We're going to introduce the terminology and some examples of probability calculations in the context of what we call bivariate distributions. We'll then also motivate some future topics by introducing the idea of Bayes' theorem towards the end of the lecture slides. So let's start off by looking at the probability of or for bivariate distributions. So first, some terminology to just rehash out and introduce. Probability as defined statistically is the likelihood that a given event, or as we'll see in our example, combination of events, will occur. There are two important rules we must follow in probability. First off, any given value of probability can range between 0 and 1, where 0 would indicate there is no chance of an event happening, and 1 would indicate the likelihood is certain for an event to occur. Further, the sum of all probabilities in our sample space must sum to 1. If either of these bullet points are violated, we know there's something wrong with the information we've been given, or it's not a true probability distribution. Most often in class, though, we will be working with known or named probability distributions. So for example, this week we're talking about the binomial or the Poisson. Next week we'll be talking about the normal distribution a lot, but we'll also introduce things like the t-distribution, and we'll see the chi-squared, exponential, and so on throughout the semester as well. The nice thing about the named distributions is that they already have these two important rules that are met, and have known properties that we can take advantage of more easily. So to review probability from some of your either past stats classes or the material available in the review week 0 portion of our site, we'll first talk about a bivariate distribution. And that's any distribution that is defined by not one, but two random variables. So for example, we could consider a case where we're looking at someone if they have or don't have a respiratory disease, which we'll call our random variable y, and also compare that to their smoking status x, if they're a smoker or non-smoker. So we could imagine that we did some study, we collected the information, and then we were able to present it in the table below, where we can see that, for example, a smoker who has respiratory disease represents 15% of the sample. And so we'll use this table and these random variables in the following slides to define some specific elements of probability. So first, let's introduce the idea of a joint distribution. Based on our bivariate distribution, we can calculate the joint distribution or joint probability for any two observed values of smoking and respiratory disease. Now, what this looks like in our probability notation is that instead of saying x equals our random variable x equals the observed little lowercase x and the random variable y equals the lowercase observed variable y, we actually have this essentially upside down cap, this intersection symbol. And so that's just to introduce some terminology there for probability that you may see in some of the textbooks out there or even online. Now really though what this is getting at is, based on our nice table here that we have set up, what's the probability that someone has both x and y is somewhat intuitive. So for example, we can ask the question, what's the probability of randomly sampling a non-smoker who has respiratory disease? So we might then look at our data over at the table here, and we'll take a second just to try and see what you might think at home before we write the answer down together here in our probability notation. And so now that you've maybe had a chance to at least look at the table and make a guess at what that probability might be, we can first write it out formally in our notation. So the probability someone's a non-smoker would be x equals 0 based on smoking status being that random variable x, and also that someone has a respiratory disease. So here then, if we see it's x equals 0 and y equals 1, we can go look over here at the x equals 0 column and the y equals 1 row. And we see now that I'm writing all over the board that it's equal to 0.05. And so that's the joint distribution, where we have these two characteristics together, and we can look at what it might be if A and B, or in our case, X and Y, occur simultaneously. This differs, though, from what we might also be interested in, which is the marginal distribution. And that's the individual probability distribution for each random variable on its own. So where we've presented the data with information in a rich fashion for both X and Y, we could imagine that we just have the information for smoking status or respiratory status from our sample, and we could calculate that probability. So in our case here, that's really representing the total column or the total row for our two random variables, where we're adding up the probability for both, let's say if you're looking at having a respiratory disease, that y equals 1 top row, we're adding those probabilities together of being a smoker or non-smoker, because for the marginal distribution for respiratory disease, we don't really care about the smoking status. So let's take a second maybe to pause the video at home and answer the questions on the screen that we'll briefly then walk through together in a second. Okay, so let's take a look first at what is the probability of randomly sampling a non-smoker. In our formal notation, we might say probability of x equals 0. And so if this did, let's say, represent the true population, we could go over to our table and look at this and say, oh, it looks like 55% or 0.55 here are people who are non-smokers. Likewise, we can do the similar approach for the question of what's the probability of randomly sampling someone without respiratory disease. And so here we would say probability that y equals 0. And then we can go over to our table here, see it equals 0.8, and write that down for our answer here in our probability notation. Yet a third way we may be interested in describing the distribution of our two random variables is through its conditional distribution. This is the probability distribution for a random variable when we're interested or know that the other random variable is at a particular value. So for example, the way we would write this statistically or in our probability notation is the probability that our random variable x is maybe some observed value x, given we already know that someone has either respiratory disease or not in our example, that y is equal to lowercase observed sample space value y. Now, this actually has then this relationship on the right-hand side of our equal sign here, where we see that it's equal to this combination of the joint and marginal distributions we defined previously. We see here that we have that joint distribution at top in our numerator, the probability that x is equal to x and y is equal to y at the same time, and then that will be divided by our marginal distribution, that y is equal to y. So if you want, we can take a second to pause the video and answer the questions on the screen here based on our data set shown again at the right-hand side, and then we'll walk through it together in a second. Okay, so for a non-smoker, or given that we know someone is a non-smoker, what is the probability of having a respiratory disease? So the way we would again write this out formally is the probability someone has that respiratory disease given that we know they are a non-smoker. We'll then use our equation above to write this out. Probability of y equals 1 and, or the intersection with x equals 0, divided by our marginal distribution for non-smokers. Now, since we're running a little tight on space here, I'm going to erase away that one formula we wrote here, just so we have some room to squeeze it all in. Except it's very, very poorly erasing right now. And what we see here then is that if we actually put those values in, we will have our 0.05 for that x is equal to 0 and y is equal to 1 over here, divided by the probability of being a non-smoker at the 55% or 0.55. And we can then do the math with R or a calculator and see we have a 9.1% probability that someone, if they are a non-smoker, would have respiratory disease. And of course, this may be more interest in clinical or actual practice, let's say, because if we already know some important feature about someone, we may be more interested then in how atypical or expected something might be. Likewise, for a smoker, what is the probability of having a respiratory disease here? So we can put the probability of y equals 1 again, but now instead of x equals 0, we'll have x equals 1. We can write out that formula more formally above, but in this case, we'll just leverage that we can mimic sort of what we did before, replacing that value appropriately with the 0.15 squiggly square going on there, divide by the probability of being a smoker for its marginal distribution of 0.45, which we can notice equal to 1/3 or approximately 0.333. So if we already know someone is a smoker, there is a higher probability of having a respiratory disease than if someone was a non-smoker. Another place these ideas or concepts come together as well is if we're interested in identifying if two random variables are truly independent. And we'll also see some of this in our testing, different statistical tests we'll talk about in subsequent weeks. But we can imagine in this point we might ask the question, well, do we think smoking and the respiratory disease are independent of one another? Perhaps there's really no causal mechanism or relationship and it's just pure chance. We can examine this statistically based on our data by this following statement that two random variables, x and y, are independent if and only if, or as we abbreviate mathematically, IFF, the joint distribution or the joint probability of x and y is equal to the product of the two marginal distributions, or conversely, if the conditional distribution is equal to the marginal distribution. So it's as if we didn't even need to condition on something. So with these definitions, pick either one you'd like and see if you can answer the question of, are x and y independent for our example? And we'll walk through it together in just a second. Okay, so let's just take the case here of our top definition. We can look at the probability of x equals 1 and y equals 1, and so we can see that above we would take the joint distribution and see if it's equal to the marginal distribution for smoker times respiratory status probability. And so we see here that we have 0.45 times 0.20, and that equals 0.09. We can somewhat easily look at this then and say, does 0.09 equal 0.15? Hopefully we note that those are very different numbers, those are not equal, and therefore x and y are not independent in our example, which, even though it is a contrived example, does make some sense for the fact of smoking status with potential respiratory disease. And so from here we're going to shift gears slightly to introduce the idea of Bayes' theorem that we're going to see applied throughout the semester, but also more broadly throughout your careers as well, potentially. So the first thing to note is that we do have a lot of names or twists on names for different things, and so it's referred to as Bayes' theorem or Bayes' rule or Bayes' law. It's all of the above are acceptable, and I've seen all of them in practice. I just most commonly call it Bayes' theorem. And so what it does is it calculates what we call the posterior probability of an event based on some prior probability by utilizing those conditional probabilities we introduced and discussed briefly before. The theorem therefore shows us how to take the prior information or expectations we have, so for example, maybe the assumed prevalence of a disease such as COVID-19, incorporate some new information we may have, so maybe we have a quick test diagnostic assay to run to see if someone may or may not be positive for COVID-19, and then we can obtain a revised posterior probability, which we also might call a predictive value or predictive probability. In 611, we're going to most heavily use this and encounter this when discussing the idea of diagnostic testing performance. So for example, sensitivity, specificity, positive and negative predictive values. And that'll be in a few weeks. However, I would like to note that this nifty theorem serves as the foundation for the entire Bayesian paradigm of statistics. And so it's quite powerful, a theorem that's really built a lot of advancement in both statistics and also clinical research and science out of it. Before we can formally define it, though, we should introduce a few extensions of things we've discussed previously and also review some important facts that are in our week 0 materials that you may have covered, albeit in different names, in past statistical courses. So the first thing that's helpful to note is just based on that definition of conditional probability from earlier, we can rearrange our terms so that that joint distribution, the probability of x and y, is actually what we're solving for. And so we see here that we can also write the joint distribution as the product of the conditional and marginal distributions. Likewise, we can also do it in different ways so that the joint distribution of x and y is equal to either the product of the marginal distribution of x times x given y, or likewise marginal distribution of y times y given x. And so for today, we're going to essentially accept this as a useful fact to apply in a few minutes. Also, before defining Bayes' theorem, it's helpful to recall what we named or have named the total law of probability. And this is found in lecture SA3, section D, in the packet for enrolled students in week 0. Essentially what this says is that for some probability x for a marginal distribution, we can represent that by the sum of x and all of its intersecting parts with some other random variable y. So in this case, we're leaving it more generic or abstract, that y can be from 1 to k, but with our bivariate distribution, we can note that really in that case, k just equal 2. And so what we see here is that we're also tying together that joint distribution with what we just saw in the previous slide of the conditional times the marginal. So again, a helpful fact just to keep in the back of our mind. So without further ado, Bayes' theorem states that the probability of x given y is equal to the probability of y given x times the probability of x divided by the probability of y. Okay, I can appreciate it's a bit anticlimactic. It's essentially just a fancy way of combining different conditional and marginal distributions and probabilities together in this randomly seeming way. However, there are a lot of really interesting applications, and so the one that we're really going to see most in depth in 611 in a few weeks is the diagnostic testing framework. So just to help motivate that and maybe get you thinking or excited for this in a few weeks, let's just define two new random variables where d sub I is going to represent I mutually exclusive and exhaustive disease states that we might be trying to test for, where I could be, 2, or it could be any number of them. And we'll say t represents some test or a presence of a symptom. So then what Bayes' theorem would state is that, well, the probability you have the given disease of interest, given you have a positive test or assay or some symptom present, is going to be equal to this application of joint or conditional probabilities and marginal probabilities. And we see here these two different equality signs are by some of those facts we've previously stated before. Again, it might look a bit foreign now, and don't worry about that. We'll really dig into it in a few weeks. But I just want to introduce it to give you an idea for what's taking place. And so with that, you're free to turn off the video now or re-review any of the material that was covered in this lecture, unless you're interested in hanging out for a few more seconds to hear about some of the potential of Bayesian analysis based on Bayes' theorem. Okay, I gave you an out. I gave you the chance to leave before I change your life to talk about Bayes' theorem as applied with Bayesian statistics. I will admit this is somewhat beyond the scope of 6611 just based on the volume of material we have to cover in the semester, but I think it's really important to at least introduce the roots of Bayesian analysis in practice so you're exposed to the ideas, and also just to get an idea of how widely applied Bayes' theorem is in different contexts. So let's, for the sake of thinking like a Bayesian, let H represent a hypothesis to be tested. And we're going to let D represent the data which may give evidence for or potentially against that hypothesis of interest. Then based on Bayes' theorem, we have this nice combination that given the data we observe here, what's the probability that hypothesis seems realistic? And that can therefore be represented through Bayes' theorem as the probability of the data given we expected a certain hypothesis and the marginal distributions of that hypothesis in the data. Now, more specifically, each of these terms plays a different role in Bayesian statistics that we think and talk about in a specific way. That probability of the hypothesis, or P sub h, is what we call the prior probability that the hypothesis is true before the data was considered. This is one of the tricky things about Bayesian statistics that get people hooked up a bit, is that idea of having to define some prior belief and either being too strong or too vague about that definition. The probability of D given that hypothesis H is what we would call the likelihood and represents the evidence for the hypothesis provided by our observed data D. The probability of D is that total probability of our data, which takes into account all the infinite possible number of hypotheses. Don't worry, we have some ways of addressing that in Bayesian statistics. And finally, of interest is the probability of H given D, or that posterior probability that the hypothesis is true after the data has been considered. And so if at any point later on you'd like to talk more about Bayesian statistics or learn some more, I'm always happy to chat, but I just want to introduce it briefly, not as something we'll really focus on or see much of in 611, but just so you're aware of the wide world out there of statistics. So with that, I'll truly end the lecture this time, and I hope you have a great rest of your day.